Alright, exercise 2. So, before we get into this proof, I wanted to include this little bit right here. Because in the hint it says the answer is not when x and y are linearly dependent. And the reason you might think that is that if you look back at the proof of 1-13, which is this thing right here, you see, oh, well, the only place we have an inequality is here. And we know that these two things are literally the exact same, and these two things are literally the exact same, this here. And so, therefore, the inequality has to come from here. And so, equality holds when these two things are equal. And so you might think, oh, well, when are these two things equal? Oh, well, if you just cancel out the 2, then you have this sum has to be equal to this multiplication. Oh, but we have this right here, and this holds if and only if x and y are linearly dependent, so we're done. But that's not the right way to think about it, or that's just wrong, because you've got these absolute value signs here. And so what you need is you need to know when this thing without the absolute value is equal to norm of x dot norm of y. Knowing this here is not enough. So let's delete this and go with this. So by the proof of 1-13, we see that equality holds. Here, I'll write it out. T holds if and only if the sum from I equals 1 to n of that. Here, I'll write it with subscripts because I think that's a little easier. When this is equal to 2x dot y. See here. So now this is we call that the sum from I equals 1 to n of xi, yi is by definition the inner product of x with y. So we want to show that these two things are equal. We know that now this looks like a little kind of out of like where am I getting this from, but it will make sense later on. We know, well, if we were to write this out, this is this inner product, which is just if you were to if you were to like FOIL this out, which you can do because inner products are linear, you'd end up with the inner product of x with x, which would just become norm x squared, plus you'd also get minus the inner product of y with y, which becomes plus norm of y squared, and then you would subtract twice the inner product of x and y. And by the law of cosines. Now remember what the law of cosines says. If we have a triangle, any triangle, and this is A, this is B, this is C, and this angle here is theta, then c squared equals a squared plus b squared minus 2ab cosine theta. That's just something from more basic math. You can go back and look this up and go look up a proof of this. But if we were to put this in terms of, let's say we wanted to look at an angle or like vectors x and y. So let's say this is like the origin here. Instead of a, b, and c, we have this is this is the vector x and this is the vector y. And so then this length, this is the norm of x, this length here is the norm of y, then this side here would be x minus y. And so then what does the law of cosines say? It says precisely that the norm of x minus y squared is equal to norm x squared plus y squared minus 2xy cosine theta, where theta is the angle between x and y. So here, let's erase all this now that we've got this. And so, look, this means that the inner product of x with y, oh, there shouldn't be a 2 there because we cancel the 2 out. This is equal to norm x dot norm y if and only if well, before we get there, let's combine these two equations. So if x minus y squared is equal to this and this, we cancel the x squared, we cancel the y squared, we cancel the minus 2. So inner product of x with y is equal to norm x dot norm y cosine theta. And thus, we have inner product of x and y is equal to norm x dot norm y if and only if, well, looking at this previous equation, we need cosine of theta to be equal to 1. But when does that happen? If we're just looking at the unit circle, then that happens if theta is, I'll just say it's equal to 0. Yeah, so this happens only if theta is equal to 0. And so when can this happen? This means that, like, if you've got the 0 and if you've got x going this way, then y also has to go this way. Or if x is going this way, then y also has to go this way. So basically what we're saying here is that x and y have to be a positive scalar multiple of each other, or at least a non-negative multiple of each other. Because if you could have either x or y be 0, and that still holds. So this is if and only if y is a non-negative constant multiple of x. And so that's kind of like saying that they have to be collinear, but like if you had x pointing this way, y pointing this way, then this angle, that would be pi, and so cosine of pi is -1, and that's not what we want. So they have to be pointing in the same direction, so it's stronger than being collinear. But anyways, there we go. That's when equality holds, and this completes the proof.